In this lesson, we speak about the derivative as a function. In previous lessons, we defined the derivative of a function at a particular point within the domain of that function. Now we will we will explore the derivative as a function from function f by considering the limit at every single point x in the domain of f. So let's start with a definition. So this is what we have. The derivative of the function f of x with respect to the variable x is the function f prime. That's how we say that, f prime, whose value at x is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided the limit exists. So you recognize this. Now the difference between how we're using this definition now is before we had this definition for the derivative of a function at a particular point. So we had f of x naught plus 0 minus f of x naught, right? And so now it's just f of x plus h minus f of x, where x is some value at actually any point in the domain of our function. Now, if f prime exists at a particular x, then we say that f is differentiable at x. That is to say, it has a derivative at x. If f prime exists at every point in the domain of our function, then we say that our function is differentiable. What we will now do is we will consider a function and we will find its derivative. So let's do that now. All right, we want to differentiate this function f of x is equal to x over x minus 1. That is to say, we want to use the definition of our derivative in order to find the derivative of this function. All right, so here we go. So f prime, there we go. F prime of x will be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is what you and I are calculating. All right, so let's do that now. This is equivalent to the limit as h approaches 0 of, now f of x plus h, we know that means we need to substitute x plus h into our function for both of those input variables. So now you have x plus h over x plus h minus 1 minus f of x, right? I'm here now, minus f of x. So it'll be minus x over x minus 1. And then all of this over h. All right, our job now is to simplify. We can simplify the numerator by getting common denominators. The LCD is x plus h minus 1 times x minus 1. So what this means is this first fraction will have to be multiplied in the numerator and in the denominator by x minus 1. This fraction here will have to be multiplied in the numerator and in the denominator by x plus h minus 1. Let me see if I can show that now. I'm going to scroll up here. All right. So then what that gives us is f prime is equal to the limit as h approaches 0 of x plus h times x minus 1 all over x plus h minus 1 times x minus 1 minus x times x plus h minus 1 over x minus 1 times x plus h minus 1. And then all of this is over h. Now, we have common denominators in the numerator, so we can now combine these two terms. So then this is equal to the limit as h approaches 0 of, let's expand these binomials. So then I'm going to do a few things at once, folks. I am going to expand this binomial by distributing. I'm going to distribute a negative x here, a negative x, and I'll put all of that over the same denominator. So that'll give me x squared minus x plus xh minus h minus x squared minus xh plus x. And all of this is over that LCD x plus h minus 1 times x minus 1, and all of that is over h. Now, notice that x squared and negative x squared are opposite, so they cancel. Furthermore, xh and negative xh cancel, and negative x and positive x cancel. And so then we have the limit as h approaches 0 of, we have negative h over this LCD, which is x plus h minus 1 times x minus 1, and then all of that divided by h, which is equivalent to multiplying by 1 over h. Now notice that these h factors divide out, and you are left with f prime of x is equal to the limit as h approaches 0 of negative 1 over x plus h minus 1 times x minus 1. Now, the denominator for once of this expression is no longer 0 when we use direct substitution. So let's go ahead and directly substitute here. Let h become 0. And what this equals is negative 1 over, if you let h be 0, then this is x minus 1 times x minus 1. So then this is x minus 1 quantity squared. So this, folks, is f prime of x. This is the derivative of our function f. So this is f prime. Let me reiterate that. This is f prime of x. Good job. All right, a brand new example. Find the derivative of this square root function. F of x is equal to the square root of x, of course, for positive values of x. After we find the derivative function, now remember the derivative is a function, we will use that derivative function to find the tangent line to the curve y equal to the square root of x at x equal to 4. All right, so let's first find the derivative of this function. So here we go. F prime of x is equal to, let's use our definition, the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so then f prime of x is equal to the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. We cannot use direct substitution, at least not yet, because then this would be undefined. So let's continue to simplify. The way I'm going to simplify this is by multiplying by the conjugate of the numerator. So remember, the conjugate of this radical expression is just the opposite operation. So really I'm multiplying by 1 in the form of the conjugate of the numerator over the conjugate of the numerator, right? So in essence, I'm multiplying this entire expression by 1. All right, cool. Let's continue. What this does for us is it gives us the limit as h approaches 0 of, all right, here, the square root of x plus h times the square root of x plus h is just x plus h. And then notice, please, that this outer product and then this inner product cancel. Okay? And so all that's left is negative root x times positive root x, which is negative x. The denominator is h times the square root of x plus h plus the square root of x. Okay? In the numerator, x and negative x are opposites, so they cancel. And so you have the limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. And now I hope you see that the h in the numerator divides out with the h in the denominator. And so then what we're left with is that f prime, the derivative function, is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now, our expression is no longer undefined when we use direct substitution. So let's do that. Remember, h is approaching 0, so if this h is becoming 0, then this is the square root of x plus the square root of x. So then it is 1 over 2 times the square root of x. Now this is the derivative function, everybody, the derivative function. This gives us, actually I'm going to write it down because I think it's so important. Let me write it like this. F prime of x is equal to 1 over 2 root x. And what this derivative function gives us is the slope of our curve at any point. At any point. So remember, the second part of this is they asked us to find the slope of the curve at x equal to 4 at a particular x value. They actually said it like this: find the tangent line to the curve. Well, in order for us to find the tangent line, we need to find the slope, right, everybody? We know that you cannot write the equation for a line, for a tangent line, unless you know the slope of that line. So what I'm going to do is I'm going to use this derivative function to find the slope of that tangent line at x equal to 4. Now remember, they gave you x equal to 4, so f prime at 4 is 1 over 2 root 4, so then this is 1/4. What is this? This is the slope of the curve at x equal to 4. So now that I know my slope, I can come up with the equation for this tangent line. Do you remember point slope form for a line? It is y minus y sub 1 is equal to m times x minus x sub 1. Now, y minus, now what is the y coordinate for the point we're considering? Well, don't forget that they gave us x equal to 4. So f of 4 is the square root of 4, which is 2. So your coordinates are 4. They gave you that value, right? They gave you x equal to 4. When x is 4, y is 2. So in the point slope form, this is like x sub 1 and this is y sub 1, okay? So then it'll be y minus 2 is equal to the slope that we found, 1/4, times x minus 4. So then the equation for the tangent line at x equal to 4 is 1/4 x plus 1. This is the equation for the tangent line to our curve at x equal to 4. Now, for notation purposes, we're using this f prime of x to denote the derivative of a function, but it's also written sometimes as y prime, and it's also written like this, the derivative of y with respect to x, so dy over dx. Sometimes it's written like this, the derivative of f with respect to x. These are all different ways to write it. Or it's d dx of f of x. And those are probably the most common ways for us to write the derivative. Honestly, these first three ways are probably going to be the three ways that I use most often. Okay? All right, very good. All right, check this out. Show that the absolute value function is differentiable from negative infinity to 0 and on 0 to infinity, but it has no derivative at x equal to 0. Okay, so in order to show this, let's consider the graph of this function. We should all remember that the absolute value function has a graph that is a V shape. Now, if we look at the right branch, this branch here is for x values that are positive, and this branch here is linear. All right? The same goes for this branch. For x values that are negative, this branch is also linear. Notice that this branch for positive x values has the equation y equal to x. This branch here for negative x values has the equation y equal to negative x. So for positive x values, meaning this part of the graph, the derivative of the absolute value of x, right? The derivative of the absolute value function is equivalent to the derivative of just x. Because remember, x is positive. So the absolute value of x is the same as x. Now, this here is the identity function. And so therefore, the derivative is just equal to 1. All right? So what we just determined now is that for this branch here, y prime is equal to 1. Now, what about for negative values? Now, for when x is negative, of course, we're talking about this branch here. It's also linear, but the derivative of the absolute value of x is equivalent to the derivative of negative x. And that's because x is negative, right? So if x is negative, then the opposite of negative x is positive x, which is equal to the absolute value of x. That is to say, remember, x is negative, so there's going to be two negatives here, which make a positive x. So that's what the absolute value of x is. So these two are equivalent. So then we know this is the identity function whose leading coefficient is -1, right? And so then this is just equal to -1. So what we just determined here is that over here to the left of 0, y prime is equal to -1. Now, that makes sense, doesn't it? Because this is a line, this part here is a line whose slope is 1. That's why the derivative is 1, because the derivative gives us the slope of the curve. For here, for x values that are negative, the derivative is -1. Well, that makes sense because -1 is the slope for this line. Now, what we want to say now is there is no derivative at the origin. Why not? Because the one-sided derivatives differ there. From the left of 0, the slope or the derivative is -1. From the right of 0, the slope or the derivative is +1. So consider this, the right-hand derivative of the absolute value of x at 0 is equal to the limit, let me get the right marker here, there we go, is equal to the limit as h approaches 0 from the right, which is equal to the absolute value of 0 plus h, right? Let me get rid of this here, if I can. There we go. Minus the absolute value of 0, right? All over h. And this is equal to the limit. Let me write it down here. Move this up a little bit. This is equivalent to the limit as h approaches 0 from the right of the absolute value of h over h. But remember that this is to the right of 0. So your x values are positive. So therefore, this is equivalent to the limit as h approaches 0 from the right of simply h over h. So this is the limit as h approaches 0 from the right of 1, which is a constant. So this is equal to 1. Now what I would like to show you is that the left-hand derivative is different. The left-hand derivative is negative 1. Now, the left-hand derivative of the absolute value of x at 0 is, let me just change the color so that we could differentiate what we did earlier from what we're doing now, is the limit as h approaches 0 from the left of the absolute value of 0 plus h minus the absolute value of 0 over h. Now, we already did this, so this is equivalent to the limit as h approaches 0 from the left of the absolute value of h over h, which is equivalent to the limit as h approaches 0 from the left. Now remember, if h is approaching 0 from the left, that means h is negative. That means the absolute value of h will be equal to the opposite of h, right? The opposite of a negative value is positive, right? So anyway, this is equivalent to the limit as h approaches 0 from the left of negative 1, which is equivalent to negative 1. So again, I'm trying to re-emphasize that this function is not differentiable at x equal to 0. Why? Because this left-hand derivative is different from this right-hand derivative. All right, so we have proven that this function is only differentiable to the left of 0 and it's differentiable to the right of 0, but not at x equal to 0. Okay, let's determine whether this function, f of x is equal to the square root of x, is differentiable at x equal to 0. Now, let's consider the graph really quickly. Now, we know the graph of the square root function looks like this. I'll just do a quick sketch of the graph. This is the graph of the square root function. Okay, so notice that the square root function is not defined to the left of 0. Now, furthermore, you and I already found f prime of x earlier. There we go. F prime of x, of course, means the derivative of the square root of x. And we found that to be 1 over 2 root x. Now the question is, does this exist at x equal to 0? Does the derivative exist at x equal to 0? Look at the definition. The limit as h approaches 0, of course, from the right, because the function's not even defined over here on the left, it'll be 0 plus h minus the square root of 0 all over h, right? So this would be equal to the limit as h approaches 0 from the right of the square root of h over h, which is equivalent to the limit as h approaches 0 from the right of 1 over the square root of h. Now, here you can see that if we allow h to approach 0, then this value down here is getting smaller and smaller and smaller, of course, while the numerator is fixed at 1. Therefore, this ratio is approaching infinity. So what we just determined is the right-hand limit, which is what this is. The right-hand limit is not a real number. It's not finite. Therefore, there's no derivative at x equal to 0. Now, what I would like to do my very best drawing for you is what's happening to these secant lines as h approaches 0. So the secant line, watch this. Now let's see if I can do the best that I can. The secant line is here for this point here and the origin. But if the point gets closer to the origin, now the secant line, here I can change the color so it can pop out a little bit. The secant line is here, which means the slope is now even greater. If the point moves even closer to the origin, now the secant line is here. And the closer, that's really sloppy, but the idea is the closer h becomes to 0, right, then the slopes of the secant lines is approaching infinity, right? The slopes keep getting bigger and bigger and bigger, which means that the graph has a vertical tangent line, right? These slopes are, these secant lines are approaching a vertical tangent line. And the slope of a tangent line that is vertical is undefined, right? The slope of a vertical line is undefined. So as this point here approaches the origin, that is to say, as h approaches 0, then these secant lines are getting really close to a vertical tangent line at x equal to 0, and the slope of such a line is undefined. So that's so important to note that the graph has a vertical tangent line at the origin. All right, I think we need to explore this just a little bit more. When does a function not have a derivative at a point? When is a function not differentiable at a particular point? So the first case that we would like to consider is kind of what we just talked about, is a function does not have a derivative wherever there's a corner. So think about that absolute value function where we had that V-shaped graph where the one-sided derivatives were not the same, they were not equal. That's an example of when a function is not differentiable at a point. So if you have a corner, so something like, I'm just making this up, so something like this, if this is your point P right here, and you're considering the secant lines, let's say this is point Q here. Let's say point Q with a negative sign, and then let's say point Q with a positive sign, so that we're allowing we're considering the derivative to the left of P and the derivative to the right of P. Now notice that the derivative, let's see, the secant line would look something like this, and of course this is really hard to show, but as we allow this point Q to approach point P, really what's happening is that these secant lines are moving in that direction, and so these secant lines are becoming more and more and more positive in essence, right? And so, but from the right, as this point here approaches point P, you can see here that the secant line, let's see if I can do this in another color so that it's clear. There's my sloppy secant line, okay? But as this point Q approaches point P, then we have a different secant line and a different secant line. I'm trying to be dramatic here, but these lines are approaching, are going in that direction, these secant lines. The point of the matter is these one-sided limits are not the same, and notice the slopes of these secant lines to the right of P is very different than the slopes of the limit of the slopes of these secant lines to the left of P. That's why we're saying the one-sided limits or the one-sided derivatives are different. That's why this function would fail to be differentiable at this point P. Another case where a function will not be differentiable is at something called a cusp. A cusp. This is where the slope of PQ approaches infinity from one side and negative infinity from the other side. So let me see if I can show you. This would be an example of a cusp. So notice what the secant lines are or how they're behaving as we allow Q to approach P from the left. Notice how the slope of PQ, the secant line, approaches positive infinity. Watch this. So you have this secant line here, right there, and then you have this secant line here, and then the secant line here. Notice how the secant lines are becoming more and more vertical, right? More and more vertical. I guess I could do it one more time if you'd like. There are becoming more and more vertical as Q approaches P. The secant lines are moving in that direction, right? Whereas from the other direction, so these slopes here, from left to right, of course, these slopes are positive, so they're going toward positive infinity. But from the right, something else is happening, right? As as Q approaches P from the right, there's your secant line. That slope is negative, right? And the further or the closer point Q gets to point P from the right, these lines are becoming more and more vertical, but they're all still negative, right? So negative infinity because we're reading it from left to right. So these secant lines are moving in that direction. And all of these lines have negative slope. So the slopes of these secant lines are approaching negative infinity. All right, let's look at another case of when a function is not differentiable or does not have a derivative at a point. Another case when a derivative does not exist is at a vertical tangent line. When the graph has a vertical tangent line, that is to say, when the slope of PQ approaches infinity from both sides or negative infinity from both sides. So consider as point Q approaches point P from the left. Let's look at these secant lines, okay? So here is your secant line like that. And as point Q approaches point P, notice what's happening here, there, and there, and there, and there, right? And so the closer point P gets to point Q, the more vertical this line is becoming, right? And from the other direction as well, as point Q gets closer and closer to point P, these secant lines, let's see if I can do this in another color so that it's not horribly sloppy. There's your first secant line. And then here's another secant line, another secant line, another secant line. And I hope you can see that, let's see, as this point Q approaches point P, your secant lines are moving in that direction. As this point Q approaches point P from the right of P, these secant lines are moving in this direction like that. But either way, you should see that as that happens, you get this vertical tangent line at P. And remember, the slope of a tangent line is undefined. We conclude our lesson with this important, so important statement, this theorem, that differentiability implies continuity. If f has a derivative at x equal to c, then f is continuous at x equal to c. So if f is differentiable, then f is continuous. The contrapositive is also true. So what this theorem is saying is that if f is differentiable, then f is continuous. Now, the contrapositive of a statement is always true. If a statement is true, then its contrapositive is also true. I should say it that way. If a statement is true, its contrapositive is also true. So, if f is differentiable, then f is continuous is equivalent to if f is not continuous, then f is not differentiable. Now, what we have to be super careful about here is that the converse of this statement here, that differentiability implies continuity, the converse is not true. Let me write down the converse. This is the converse. If f is continuous, then f is differentiable. That's not necessarily true. So what we are saying is if f is differentiable, then f is continuous. But the other way around is not necessarily true. If f is continuous and f is differentiable, not necessarily true. I can use the same example that you and I looked at earlier, the absolute value function. The absolute value function is this V-shaped graph. This is continuous over its entire domain. The domain is all real numbers. So this function is continuous at every point in its domain. However, it's not differentiable here at x equal to 0. Remember that? So just because you're continuous doesn't mean you're differentiable. But the theorem is saying if you're differentiable, that must mean you're continuous. To drive home this point, let me give you an analogy. If I live in California, then I live in the United States. Now, that's a true statement, right? That's a true statement. If I live in California, then I live in the United States. The contrapositive is an equivalent statement, meaning if this statement is true, which it is, if I live in California, then I live in the United States. That's true. Its contrapositive is also true, which says if I don't live in the United States, then I don't live in California. So that's also true. But what is not true is the converse of our original statement. Remember, our original statement is if I live in California, then I live in the United States. But listen to the converse. If I live in the United States, then I live in California. That's not necessarily true. It could be true, but it's not necessarily true. If I live in the United States, I can live in Kansas. I can live in Texas. I can live in Florida. Just because I live in the United States does not necessarily mean I live in California. So if you know a statement is true, its contrapositive is also true, but its converse is not necessarily true. So we have the statement that if a function is differentiable, then it is continuous, which also means that if it is not continuous, then it's not differentiable. But what we are not allowed to say is that if a function is continuous, then it's differentiable. This is an example of how that's not true. So just be careful. Differentiability implies continuity, but continuity does not imply differentiability.